Tonight, we're going to talk about a direction you have never once looked toward. Not up, not down, not toward any star you could name. A direction perpendicular to everything you know, perpendicular to the sun itself, perpendicular to the quiet path our entire solar system carves through the dark. You have spent your whole life inside a flat disk of light and motion without ever asking what waits, above it or below it, in the silence no one talks about. Here's the thing most people don't realize. Every planet, every moon, every comet you have ever heard of moves along the same thin plane, spinning together like dust caught on the surface of still water. But turn that water on its side just once, and something changes. The crowd disappears. The noise fades. What remains is emptiness so complete, so total, that only one spacecraft in human history has ever dared to fly through it. By the end of tonight, you're going to understand exactly why that emptiness exists, what it reveals about the hidden architecture of our solar system, and why the space perpendicular to our orbit is so much stranger and so much more exposed than the crowded plane we call home. Billions of miles of nothing, a sphere of ancient debris older than the sun's own light, and a silence that, once you understand it, you will never look at the night sky the same way again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Close your eyes for a moment and picture the solar system the way you have always imagined it. Planets circling the sun in wide, graceful loops, moons trailing behind their worlds like quiet companions, comets streaking through the dark on long, looping paths. It feels vast. It feels three-dimensional, endless in every direction, stretching outward with no particular shape at all. But here's the thing most people don't realize. Almost none of it is spread out evenly through space. Almost all of it lies flat on a single plane, like pieces arranged carefully on a table, rather than scattered through a room. This plane has a name. Astronomers call it the ecliptic, and once you understand what it means, you will never look at a diagram of the solar system quite the same way again. It is not just the Earth's orbital path around the sun, it is the shared roadway that nearly every major object in the solar system follows. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of them orbit within just a few degrees of this same imaginary sheet, stretched across billions of miles of space. Picture a vinyl record spinning slowly in the dark, its grooves catching a faint gleam of light. Now imagine that every planet you've ever heard of is a grain of dust resting somewhere on its surface, circling the center together, never straying far from that flat, spinning plane. 8 worlds, one shape, a single quiet agreement written into the architecture of everything around the sun. You would think, given how vast space is, that the planets would have ended up anywhere, above the sun, below it, at steep angles to one another, scattered like stars in the night sky, indifferent to any shared direction. But they didn't. And that fact alone should feel strange to you once you actually sit with it. 8 planets, hundreds of moons, thousands of asteroids, all falling into roughly the same flat arrangement, all bound to a plane so thin that if you shrank the solar system down to the size of a dinner plate, the disk of the planets would be thinner than a sheet of paper. Complete alignment, not by coincidence, not by chance, by something far older and far more physical than most people ever stop to consider, something written into the solar system before a single planet had even finished forming. And yet, here's the unsettling part. If almost everything lies flat on this one plane, then something else must also be true, somewhere just outside our ordinary field of view. There must be a direction, perpendicular to that plane, where almost nothing lies at all. Not planets, not moons, not the familiar clutter of rocks and ice that fills the ecliptic like traffic on a crowded road. A direction straight up from the disk and straight down from it, running through empty space in a line that very few spacecraft and almost no human attention has ever followed. You have spent your entire life aware of the solar system's width, its familiar sideways sprawl of planets and moons. Tonight, we're going to talk about its height, or rather, its almost complete absence of one. Think about how you experience the solar system, even without realizing it, every single time you glance upward at night. When you look up at the sky, you're usually looking along the ecliptic, because that is where nearly everything worth looking at happens to be. The planets rise and set along a predictable band of sky, the same band that the sun and moon travel through night after night, year after year. Astrologers even divided that narrow strip into 12 constellations, the same 12 you have heard named 1,000 times, without ever asking why they cluster the way they do. That entire tradition exists because of the ecliptic, because everything visible, everything moving, everything bright enough to track with the naked eye, sits inside that same thin ribbon of space stretched across the sky. You have been trained, your whole life, without ever choosing it, to look only sideways along that one familiar line. But space does not end at the edges of that ribbon. It continues upward and downward in directions almost nothing has ever been built or launched to explore. And this is where the mystery begins to take shape. If the plane of the solar system is so crowded, so busy with rock and ice and metal and dust, drifting together in that same shared orbit, then what does the space perpendicular to it actually look like? Is it simply more of the same, thinning out gradually the farther you travel? Or is it something else entirely, something colder, something emptier, something almost violently different from the plane we call home, waiting quietly above and below everything you have ever known? Here's a way to feel the scale of what we are really talking about. Imagine standing at the very centre of a vast, dark stadium, one so large that its outer walls sit billions of miles away in every direction. Now imagine that every seat in that stadium, every single one, is crowded onto just one narrow ring around the field, while the towering space above the seats, all the way up to the distant roof, sits entirely, hauntingly empty. That is the shape of our solar system. That is the strange geometry hiding in plain sight above your head every single night, disguised as ordinary darkness. We rarely think of the solar system this way, because nothing in our daily experience prepares us to. We live on a spinning ball inside that same flat plane, moving along with everything else in perfect formation. From where you stand, the disk does not look like a disk at all. It simply looks like the sky, ordinary and familiar, stretching out in every direction as if it were the same everywhere you look. But it is not the same everywhere, not even close. Somewhere above the plane of the planets, and somewhere below it, lies a region of space almost entirely stripped of the debris that fills our immediate neighbourhood, a region shaped less like a crowded highway and more like open, silent countryside. Tonight, we're going to travel there together, one careful step at a time. We will start with the reasons this flat shape exists in the first place, tracing it back to the earliest moments of the solar system's birth. And then slowly, we will turn our attention upward and downward toward the direction almost no one ever thinks to look. To understand why almost nothing exists perpendicular to the sun's orbit, you first have to travel back. Not just years or centuries, but billions of years, to a time before the sun even existed as the steady, glowing presence you know today. Before Earth, before Mars, before a single planet had taken shape anywhere in this part of the galaxy, there was only a cloud, a vast, cold, drifting cloud of gas and dust, spread out across a region of space so large it is almost impossible to picture, quietly waiting for something to disturb it. This cloud had no particular shape. It was not flat. It was not a disk. It was closer to a slow, formless fog, hanging in the darkness between stars, made mostly of hydrogen, laced with fine grains of dust left behind by older stars that had lived and died long before. For a long time, nothing happened. The clouds simply existed, spread thin across the void, cold and dark and almost perfectly still. And then, somewhere within that stillness, something shifted, quietly at first, in a way that would eventually shape everything that followed. Perhaps a nearby star exploded, sending a shockwave rippling outward through the gas. Perhaps the clouds simply grew dense enough in one small region for gravity to begin pulling it inward on its own. Whatever the trigger, the effect was the same. Gravity began to win. Slowly, almost imperceptibly at first, the cloud began to collapse in on itself, pulled inward by the combined weight of its own gas and dust, drawing closer together with every passing year. And once that collapse began, something remarkable happened, something written into the basic physics of motion itself. Every cloud like this has some tiny amount of rotation, some faint spin, even if it is far too slow to notice at first. It might come from the pull of a distant star, or the slow churn of the galaxy itself, or simple randomness in how the gas happened to be moving. Whatever its source, that spin does not disappear as the cloud collapses. Instead, it becomes exaggerated, the same way a spinning ice skater speeds up when she pulls her arms in close to her body. As the cloud shrank, it began to spin faster and faster and faster still. Here's the thing most people don't realize about spinning objects collapsing inward. They do not shrink evenly in every direction. Along the direction of the spin's own axis, matter can still fall inward relatively easily, because nothing is fighting against that motion. But perpendicular to the axis, in the plane of the spin itself, a different force comes into play. Centrifugal effects, the same outward push you feel on a fast-spinning carnival ride, begin to resist the inward pull of gravity, holding material out and away from the rapidly forming center. The result of this tug-of-war between gravity and spin was almost inevitable once you understand the physics involved. The cloud flattened. It collapsed quickly along the direction of its rotation axis, because nothing was resisting that collapse, while gravity pulled that shrinking material downward and upward simultaneously, crushing the cloud into an increasingly thin layer. But in the plane perpendicular to that axis, the spin held everything out in a wide, slowly rotating disk, unable to fully collapse. What had once been a formless, three-dimensional cloud became something else entirely. A spinning, flattened disk, glowing faintly with heat, circling an increasingly dense and brilliant center. That center, of course, became the sun. As gravity crushed the innermost gas together, pressure and temperature climbed to extraordinary levels. Tens of millions of degrees, hot enough and dense enough to ignite nuclear fusion at the very heart of the collapsing cloud. A star was born, and it lit up the disk of gas and dust still spinning around it, illuminating billions of miles of material that had not yet found its final shape. This is the moment the flat plane we now call the ecliptic first came into existence, encoded from the very beginning into the shape of the solar system's birth. Everything that formed afterward, every planet, every moon, every asteroid, inherited that same flattened shape, almost automatically. The dust and gas remaining in the disk began to clump together, slowly at first, tiny particles sticking to one another through weak static and gentle collisions, gradually building larger and larger bodies over millions of years. Because all of this material was already confined to the thin, spinning disk, everything it built was confined there too. There was no leftover cloud above or below the disk to form planets in those directions, because gravity and rotation had already stripped that material away, pulling it inward into the flattened plane. Think of it like a potter shaping wet clay on a spinning wheel. As the wheel turns and the potter's hands press gently inward, the clay does not stay in a rough, shapeless lump. It spreads outward and flattens, forming a wide, thin disc shaped entirely by the combination of spin and inward pressure. The solar system formed in almost exactly the same way, except the potter's hands were gravity itself. and the spinning wheel was the natural rotation of the original cloud, set in motion long before the sun ever existed as a star. This is why the planets orbit in the same direction, and roughly the same plane, and why their motion feels so orderly compared to the apparent chaos of deep space. It is not a coincidence that Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all trace paths within a few degrees of one another. It is the direct physical consequence of forming from a single flattened disk, spinning around a single center, obeying the same basic rules of gravity and rotation that shape spinning clouds everywhere in the universe. Order, not chance. Physics, not luck. But here is the detail that most people never stop to consider. The detail that quietly sets up everything we are about to explore together. If the disk itself formed because material was pulled inward and flattened along the plane of rotation, then the region directly above and below that disk perpendicular to it would have been swept comparatively clean from the very beginning. Not because it was forbidden territory exactly, but because there was simply nothing left there to build with. Whatever gas and dust had once occupied that space had already been dragged inward, crushed down into the spinning plane that eventually became the ecliptic. So when you look up at the night sky and trace that familiar band where the planets rise and set, you are not just looking at a random pattern in the heavens, you are looking at the literal fingerprints of the solar system's birth, frozen in place for over 4.5 billion years. And when you imagine the space perpendicular to that band, the direction few instruments have ever pointed toward and even fewer spacecraft have ever explored, you are imagining the leftover emptiness of that same violent, beautiful collapse. A region shaped not by what was placed there, but by what was pulled away, billions of years before anything alive was here to notice. There is a direction in space that has no name you would recognize, no constellation attached to it, no mythology built around it. You've never been told a story about it. No ancient civilization built a monument aligned toward it, the way so many aligned their temples and stone circles toward the rising sun, or the wandering path of the planets. And yet this direction has existed for as long as the solar system itself, quietly perpendicular to everything you have ever been taught to look at. It runs straight up from the plane of the planets, and straight down from it, through space almost nobody has ever paused to consider. Here's the thing most people don't realize when they first learn about the ecliptic. If nearly everything, the planets, the asteroids, the comets, the dust, lies flattened onto that one plane, then logic demands that something else must be true elsewhere. There must be a direction where none of that clutter exists. A direction where the crowded traffic of the solar system simply falls away, replaced by something far quieter, far colder, and far less understood. Scientists call this direction perpendicular to the ecliptic, and it is exactly what it sounds like. Straight out from the flat disk at a 90-degree angle into space that has almost never been visited. Imagine for a moment standing at the exact center of a vast, spinning carousel, the kind you might have ridden as a child, lit up with lights and crowded with painted horses circling around you. Now imagine that every planet, every moon, every asteroid in the solar system is one of those horses endlessly circling at the same height, on the same flat ring, forever bound to that single spinning plane. If you were to step off the carousel and rise straight upward, lifting yourself perpendicular to all that motion, you would leave the crowd behind almost instantly. Above your head and below your feet, there would be nothing circling at all. Just open air, and then open darkness, stretching outward in a direction the carousel itself was never built to explore. That is the direction we are talking about tonight. Not sideways, along the familiar path of the planets, not toward any star you have ever wished upon, straight up and straight down, perpendicular to the great flattened disk that carries the Earth around the Sun once every year. It sounds almost too simple to be interesting. A plain right angle drawn against a spinning disk. But the moment you actually follow that direction outward, mile after mile, billions of miles beyond anything familiar, you begin to realize just how strange and how empty this part of space truly is. Here's why this direction matters so much, and why it deserves far more attention than it has ever received. Almost every spacecraft ever launched by humanity has travelled within the plane of the ecliptic, because that is where the planets are, and that is where the missions have needed to go. Voyager, New Horizons, Cassini, Juno, all of them threaded their way through the crowded plane, visiting worlds that orbit close to that same flat disk. Only one mission in the history of spaceflight was ever specifically designed to leave that plane behind, to climb upward, out of the ecliptic entirely, into the direction almost no instrument has ever pointed. Think about what that really means. We have sent spacecraft to touch the surface of Mars. We have flown past the icy moons of Saturn. We have photographed the swirling storms of Jupiter in extraordinary detail, and sailed a lonely probe past Pluto into the frozen edges of the solar system. And yet, in all of that effort, in all of those decades of exploration, we have almost never looked directly up or directly down, away from the plane that carries us around the sun. The most obvious direction in three-dimensional space is somehow the one direction we have almost entirely ignored. Why would that be? Partly it comes down to simple practicality. Launching a spacecraft out of the ecliptic plane requires an enormous amount of extra energy, because everything about a rocket's journey, from Earth's own spin to its orbital velocity around the sun, naturally pushes a spacecraft sideways, along the plane, rather than upward away from it. It is, in a very real sense, easier to travel to the edge of the solar system than it is to travel straight up out of it. The direction perpendicular to our orbit is close in distance, but expensive in effort, an irony that has kept it almost entirely unexplored. But there is another reason this direction has been so overlooked, one that has less to do with rocket fuel and more to do with human attention itself. We are creatures of the plane we live in. Every star chart, every planetarium show, every constellation you learned as a child is built around that same narrow ribbon of sky where the planets travel. We look sideways because that is where the visible action has always been, where the moon waxes and wanes, where Venus gleams at dusk, where Jupiter and Saturn parade slowly across the seasons. Nothing has ever trained us to look straight up, away from that familiar stage, into the quiet dark above it. And yet, here's the shocking part. That quiet dark is not simply empty in the boring, forgettable sense of the word. It is empty in a deeply meaningful way, a way that tells us something profound about how the solar system formed, how it evolved, and what still surrounds it at distances almost too vast to comprehend. The direction perpendicular to our orbit is not a gap in the map. It is a clue, hiding in plain sight above every head that has ever looked up at the night sky and simply followed the crowded plane instead. Tonight, we are going to follow that direction together, one careful step at a time, the way a single spacecraft once dared to do. We will learn why the sun itself has poles that almost nothing has ever observed directly. We will follow the strange, lonely journey of the only mission ever built to leave the ecliptic plane entirely, and discover what it found in the silence above and below our familiar solar neighbourhood. And eventually, we will travel outward, even further, beyond the edge of the planets entirely, into a vast, invisible shell of ancient debris that surrounds our entire solar system in a shape nothing like the flat disk we call home. But for now, simply hold this thought in your mind as you drift towards sleep. Somewhere above you and somewhere below you, perpendicular to everything you have ever known, there is a direction in space that has been waiting patiently for someone to finally look. Let's try something together, right now, while your eyes are closed and your mind is calm. Picture a coin resting flat on a table, a simple, ordinary coin, its face turned upward toward the ceiling, perfectly still. Now imagine that coin is not made of metal, but of the entire solar system, shrunk down and flattened into a single, thin disk. The sun sits at its center, small and bright. The planets are etched somewhere across its surface, tiny circles tracing their orbits around that glowing middle point. This is the view almost every diagram has ever shown you, and it feels natural because it is the view from directly above. But here's the thing most people never actually do, even after seeing that same flat diagram 1,000 times. They never turn the coin on its side. They never take that same solar system, resting so calmly, face up on the table, and tip it over 90 degrees until it stands upright on its edge instead. If you did that right now in your imagination, something remarkable would happen to your entire sense of the solar system's shape. The wide, spacious disk you were picturing a moment ago would suddenly become impossibly thin, almost invisible, a mere line balanced delicately on the table's surface. This is not just a fun mental trick, it is, in a very real sense, closer to the truth than the comfortable, wide view we usually imagine. If you could actually travel far enough away from the solar system and then curve around to look at it edge on, exactly the way you just imagined that standing coin, you would see something startling. Not a broad, generous disk stretching outward in every direction. A razor-thin line of light, almost lost against the darkness, with the sun glowing faintly at its center, and the planets reduced to barely visible points strung along that same narrow band. Here's a number that might help this feel real. The distance from the Sun to Neptune, the outermost official planet, is roughly 2.8 billion miles. And yet the entire disk of the planets, from top to bottom, perpendicular to that vast sideways distance, is almost absurdly thin by comparison. Most of the planets orbit within just a few degrees of the same flat plane, meaning that if you shrank the solar system down until Neptune's orbit was the size of a large dinner plate, the up and down thickness of the entire planetary disk would be thinner than a single sheet of paper resting on top of it. Think about how strange that really is. We tend to imagine space as this vast, three-dimensional emptiness, planets floating freely in every direction, like fish drifting through an open ocean. But the actual architecture of our solar system looks nothing like that gentle, spacious image. It looks more like a single spinning vinyl record, laid flat, with almost everything of significance confined to that one thin groove, circling the label at its center. Height and depth, in the way you experience them standing on Earth, barely exist here at all. Now, hold on to that image of the edge-on view, the razor-thin line of light, and ask yourself a simple question. If nearly everything in the solar system is compressed into that thin line, what exists above it and what exists below it? Not sideways, along the familiar direction of the planets, straight up and straight down, perpendicular to that thin glowing thread stretching across billions of miles of space. This is the direction we are slowly turning our attention toward, the direction that almost never appears in any of the comfortable diagrams you grew up seeing. Here's the thing that makes this direction so difficult to picture, even once you understand it intellectually. Human beings did not evolve to think this way. We live on the surface of a spinning planet, itself embedded in that same flat plane, moving along with everything else, in perfect formation. From where you stand on the ground at night, the sky simply looks like the sky. It does not visually announce itself as a thin disk viewed from within. The way a person standing on the surface of a vinyl record would never notice its own flatness just by looking outward along the groove. To truly understand what perpendicular to the ecliptic really means, you have to imagine lifting yourself entirely outside your ordinary point of view. Imagine floating somehow far above the Earth, far above even the Sun itself, at a height equal to the distance between the Sun and one of the outer planets. From up there, looking straight down, you would finally see the disk the way it actually is. Not a scattering of distant lights in every direction, but a tight, organized swirl, almost flat enough to seem two-dimensional, spinning slowly around the brilliant point of the sun. And then imagine turning your gaze away from that swirl entirely, looking instead straight upward, away from the disk into the space directly above your floating position. What would you see there? Almost nothing. No planets drifting past, no comets tracing familiar paths, no dust, no debris, no clutter of any kind interrupting your view. Just stars, distant and ancient, scattered thinly across the true emptiness of interstellar space, utterly indifferent to the crowded little disk spinning quietly far below. This is the strange, almost unsettling truth hiding behind that simple image of a standing coin. Our solar system does not fill space evenly, the way a comfortable childhood diagram might suggest. It occupies a startlingly narrow slice of it, a thin, glowing seam running through an otherwise vast and largely empty volume. And once you understand that shape, once you can actually picture the razor-thin, edge-on silhouette of everything you have ever known, the question of what exists perpendicular to it stops feeling abstract and starts feeling almost inevitable. Somewhere directly above that thin seam of light, and somewhere directly below it, lies most of the actual volume of the solar system's neighbourhood, and almost none of it has ever been explored. At the very centre of everything we have been describing sits the Sun, a sphere of plasma so large that more than 1 million Earths could fit inside its volume. You have seen its light your entire life. You have felt its warmth on your skin, watched it rise and set thousands of times, and yet there is a part of the Sun almost no human being has ever actually seen. Not because it's hidden behind clouds or blocked by distance, but because of the simple, geometric accident of where we happen to be standing. We view the Sun almost entirely from its side, and almost never from above or below. Here's the thing most people never think about. The Sun spins, just like the Earth does, rotating on its own axis roughly once every 25 days near its equator, slightly slower near its poles. That axis of rotation points in a particular direction, tilted only slightly compared to the plane of the planets, but tilted nonetheless. And just like the Earth, the Sun has poles, a north solar pole and a south solar pole, sitting at opposite ends of that spinning axis, largely unseen by the endless stream of spacecraft we have sent to study our star up close. Think about how strange this really is. We have sent probes to orbit the Sun, to sample the solar wind, to photograph flares erupting from its surface in exquisite detail. And yet almost every one of these missions has approached the Sun from within the same flat ecliptic plane, the same crowded highway that carries the planets around it. They observe the Sun's equator, its middle latitudes, the familiar face it turns toward the plane of its own planetary system. Its poles, the true top and bottom of this enormous, churning sphere, have remained almost entirely out of view. Why would this matter? Because the Sun is not a smooth, uniform ball of light, behaving identically no matter where you observe it from. Its magnetic field, tangled and immensely powerful, behaves differently near the poles than it does near the equator. Its solar wind, the constant stream of charged particles blasting outward into space, moves differently depending on latitude, faster and more consistent near the poles, slower and more turbulent near the equator. To truly understand the Sun, to build a complete picture of the star that makes every form of life on Earth possible, scientists needed a view no one had ever obtained. Here's a number that puts this problem into perspective. The Sun sits roughly 93 million miles from Earth, a distance already difficult to imagine. But travelling to view its poles directly does not simply mean flying that same 93 million miles in a different direction. It means leaving the ecliptic plane entirely, climbing up and out of the crowded orbital highway that every planet and nearly every spacecraft has ever travelled along. And leaving that plane, as it turns out, requires far more energy than simply flying farther away within it. Imagine, for a moment, a marble rolling along the inside of a giant spinning bowl, circling steadily around the rim without ever climbing toward the centre. To make that marble leave its circular path and rise up out of the bowl entirely requires a completely different kind of push, one working against the marble's existing motion rather than simply adding to it. This is essentially the challenge facing any spacecraft that tries to leave the ecliptic plane. Earth's own motion around the Sun and the motion every rocket inherits at launch all push a spacecraft sideways, deeper into the plane, rather than upward, out of it. Because of this, for decades, the poles of our own star remained one of the least understood regions in the entire solar system, hidden not by distance, but by the sheer physics of orbital motion. We had better maps of the far side of the Moon, better photographs of the surface of Mars than we had of the Sun's own polar regions, sitting just above and below the star that dominates our entire sky. It is a strange kind of blindness, entirely self-inflicted by the shape of our own solar system and the paths our spacecraft are naturally inclined to follow. And yet scientists knew these polar regions mattered enormously, not just out of curiosity, but for deeply practical reasons. The Sun's magnetic field, generated deep within its churning interior, flips entirely roughly every 11 years, north becoming south and south becoming north, in a process still not completely understood. Watching that transformation unfold near the poles, where the magnetic field lines converge most dramatically, could reveal secrets about solar storms, about the 11-year cycle of solar activity, and about the violent eruptions that occasionally send waves of charged particles racing toward Earth itself. Here's the thing that makes this story so compelling and so quietly dramatic once you understand what was at stake. To finally see the Sun's poles, to finally look directly down onto the north and south of our own star, humanity would need to build a spacecraft unlike almost any other. Something willing to leave the comfortable, familiar plane of the planets behind entirely, something willing to fight against billions of years of inherited orbital motion, climbing up and out of the ecliptic in a direction almost nothing had ever travelled before. It would take an extraordinary mission and an extraordinary amount of patience to finally achieve something this simple sounding and this profoundly difficult. In the coming chapters, we're going to follow exactly that mission, the only spacecraft in the history of space exploration built specifically to leave the ecliptic plane and study the Sun from above and below. Its journey was slow, indirect, almost strange in its design, borrowing gravity itself from another planet just to escape the flat plane that had confined every other mission before it. What it found once it finally reached those hidden polar regions revealed a solar system stranger, quieter, and more surprising than almost anyone had expected. But first you need to understand just how differently this single spacecraft had to travel, compared to everything that came before it, in order to finally look at our own star from a direction no one had ever truly seen. The year was 1990. On the 6th of October, a spacecraft lifted off from the launch pad, carried skyward by the Space Shuttle Discovery, beginning a journey unlike anything humanity had ever attempted before. Its name was Ulysses, borrowed from the ancient wanderer of Greek legend, a fitting choice for a mission that would travel farther out of the ordinary path than any spacecraft before it. Its goal was simple to describe and extraordinarily difficult to achieve. Leave the plane of the planets entirely and fly up and over the Sun's own poles into a direction nothing had ever gone before. Here's the problem the mission's engineers faced from the very beginning. A rocket launched from Earth inherits Earth's own motion, moving sideways through space at roughly 66,000 miles per hour, locked into that same flat, familiar plane shared by every planet in the solar system. To leave that plane entirely, to travel perpendicular to it rather than simply farther out along it, a spacecraft would need to cancel out an enormous amount of that sideways motion. Doing so directly, using rocket fuel alone, would have required more propellant than any rocket of that era could possibly carry. The mission, quite simply, should not have been possible using conventional means. So the engineers behind Ulysses came up with something remarkable, something almost poetic in its simplicity. Instead of fighting the solar system's shape directly, they decided to borrow help from one of its largest residents. Ulysses would not travel straight toward the sun's poles. It would first travel outward, toward Jupiter, using the giant planet's immense gravity to fling itself violently out of the ecliptic plane entirely, the same way a slingshot uses tension to redirect momentum in an entirely new direction. Jupiter, in effect, would do what raw rocket fuel alone never could. Think about the sheer audacity of that plan for a moment. Jupiter sits roughly 484 million miles from the Sun, itself already a staggering distance to travel. And Ulysses was not simply flying to Jupiter to study it, the way so many missions before and after would do. It was flying to Jupiter purely to use its gravity as a tool, bending its own trajectory upward, out of the flat plane, before continuing on an entirely different path back toward the Sun's polar regions. It was a journey of billions of miles deliberately designed as a detour, just to finally travel perpendicular to everything humanity had explored before. In February of 1992, roughly a year and a half after launch, Ulysses reached Jupiter and completed its dramatic gravitational slingshot. The maneuver worked exactly as planned. The spacecraft's path bent sharply upward, out of the familiar ecliptic plane, curving into a new orbit tilted at more than 80 degrees relative to the plane of the planets. For the first time in the history of space exploration, a human-built spacecraft was now traveling almost entirely perpendicular to the plane that carries Earth, Mars, Jupiter, and every other planet around the Sun. Here's what makes this moment so quietly extraordinary. Ulysses had left behind the crowded highway of the solar system entirely. It was no longer following the same road as every planet, every asteroid, every comet ever tracked by astronomers. It was climbing slowly and steadily up and out of that flat disk into the direction we have been describing since the very beginning of tonight's journey. No spacecraft before it had ever travelled this way. No spacecraft since has managed to fully repeat it either, making Ulysses, even decades later, the only mission of its kind. As Ulysses climbed higher above the ecliptic plane, its instruments began recording something almost immediately noticeable. The environment around the spacecraft was changing, quietly but unmistakably, the farther it travelled from the crowded plane below. The density of dust and debris, so common within the plane of the planets, began thinning out dramatically. The behaviour of the solar wind, the constant stream of particles blasting outward from the Sun, began shifting in ways scientists had only theorised about, but never directly measured, until this single, lonely spacecraft carried its instruments into that quiet, perpendicular darkness. By 1994, Ulysses had climbed high enough above the ecliptic plane to pass almost directly over the Sun's south pole, achieving something no spacecraft had ever accomplished before. It looked down, quite literally, onto a region of our own star that had remained essentially unmapped throughout the entire history of astronomy. And then, continuing along its long, looping orbit, it swung around and repeated the achievement over the Sun's north pole roughly a year later, completing a survey of both polar regions that no other mission has fully matched, even decades afterward. Here's the thing that makes Ulysses feel almost cinematic, once you understand the full shape of its journey. This was not a quick flyby over in a matter of hours or days. Ulysses spent years climbing out of the ecliptic plane, using Jupiter's gravity as a springboard, before spending additional years slowly completing its long elliptical orbit around the Sun's poles. The mission, originally expected to last only a handful of years, ultimately continued operating for more than 18 years, finally ending contact in 29, having completed multiple full passes over both the Sun's north and south polar regions across nearly 2 full solar cycles. By the time its mission finally ended, Ulysses had travelled billions of miles, far outside the comfortable, familiar plane every other spacecraft before it had followed. It had spent years in the quiet, perpendicular darkness above and below the solar system's crowded disk, gathering data that reshaped our understanding of the sun's magnetic field, its solar wind, and the strange, largely empty space surrounding our star from directions almost nothing had ever explored before. And what it found there, in that lonely, perpendicular silence, was stranger, and in some ways more unsettling than anyone had fully anticipated before the mission began. When Ulysses finally climbed high enough above the ecliptic plane to look directly down onto the sun's poles, scientists back on Earth did not know quite what to expect. No spacecraft had ever sent back direct measurements from this vantage point before. Every prediction, every model, every careful calculation had been built on theory alone, because there had simply been no way to test it. And so, as the data began arriving, slowly, patiently, across millions of miles of empty space, researchers found themselves reading numbers that no human being had ever seen before, describing a part of our own solar system that had remained invisible for the entire history of astronomy. The first surprise came from the solar wind itself, that constant stream of charged particles blasting outward from the sun in every direction. Within the ecliptic plane, close to the sun's equator, this wind behaves in a complicated, turbulent way, speeding up and slowing down unpredictably, tangled by the sun's shifting magnetic field. But high above the plane, near the poles, Ulysses found something remarkably different. The solar wind there moved fast, consistently fast, streaming outward at speeds far higher than anything typically observed near the equator, almost as if the poles were quietly exhaling in one long steady breath. Here's the thing that made this finding so striking to scientists at the time. It suggested that the sun does not behave uniformly across its entire surface, the way a simple glowing ball might seem to from a great distance. It behaves more like a complex layered machine, with different regions producing dramatically different behaviour depending on latitude. The poles quiet and steady, the equator turbulent and unpredictable, and almost nothing before Ulysses had ever confirmed just how stark that difference truly was, because almost nothing had ever travelled far enough out of the ecliptic plane to measure it directly. But the solar wind was not the only surprise waiting in that perpendicular silence. As Ulysses climbed farther and farther away from the crowded ecliptic plane, its instruments began detecting something almost eerie in its simplicity. The density of interplanetary dust, the fine scattered debris that fills the plane of the planets, thinned out dramatically the higher the spacecraft climbed. Within the ecliptic, this dust is everywhere. Remnants of ancient collisions between asteroids, tiny fragments shed by passing comets, an endless faint haze drifting quietly between the planets. Above the plane, that haze grew thinner and thinner until it had nearly vanished entirely. Think about what that actually means once you sit with it for a moment. The crowded highway of the solar system, filled with rock and ice and drifting fragments, genuinely does not extend very far beyond the flat plane where the planets themselves orbit. Climb high enough, travel far enough perpendicular to that plane, and the debris that fills our everyday view of the solar system simply falls away, leaving behind a region of space that feels comparatively hollow and comparatively pure, stripped of nearly everything that makes the ecliptic feel so busy and so cluttered. Here's a detail that unsettled some scientists more than they expected it to. Ulysses also carried instruments designed to detect cosmic rays, high-energy particles arriving from far outside the solar system entirely, born in distant supernova explosions and other violent events scattered across the galaxy. Within the ecliptic plane, the sun's own magnetic field partially shields the inner solar system from these particles, deflecting many of them away before they ever reach Earth. But above the plane, near the poles, that shielding behaves differently, weaker in some regions, allowing more of this ancient, energetic radiation from deep space to slip through almost unimpeded. This discovery mattered for reasons far beyond simple curiosity. It meant that our solar system's protective magnetic bubble, the vast structure known as the heliosphere that shields us from the harshest radiation of interstellar space, is not shaped like a perfect, uniform sphere. It bulges and thins unevenly, stronger in some directions, weaker in others, shaped by the same rotation and magnetic complexity that governs the sun's poles and equator so differently. Perpendicular to our orbit, in other words, is not simply empty and calm. In certain respects, it is more exposed, more directly connected to the raw energy of deep space than the crowded, well-shielded plane we call home. Here's the thing that made Ulysses's mission feel almost hauntingly appropriate, once all this data had been gathered and studied. The spacecraft had travelled into a region defined, in almost every sense, by absence. Less dust, fewer collisions, a thinner, quieter version of the busy solar neighbourhood most of us picture when we imagine the space around the sun. And yet, in that same quiet absence, it had found something more directly connected to the vast ancient universe beyond our solar system, as though stripping away the familiar clutter had revealed a thinner, more honest boundary between our small corner of space and everything else. By the time its long mission finally concluded, Ulysses had completed multiple full passes over both of the sun's poles, gathering data across nearly 2 entire solar cycles, roughly 22 years of the sun's own magnetic rhythm. It confirmed that the fast, steady solar wind near the poles remains remarkably consistent, even as the sun's overall activity rises and falls across each cycle. It confirmed that dust truly does thin out dramatically outside the ecliptic plane. And it confirmed, perhaps most strikingly of all, that the region perpendicular to our orbit is genuinely, measurably different from the crowded plane most of humanity has spent its entire history studying. And yet, even after everything Ulysses discovered, an enormous amount of that perpendicular direction remains entirely unexplored. The spacecraft's orbit, however extraordinary, still only sampled a narrow slice of the vast three-dimensional space surrounding our solar system. Beyond the range Ulysses ever reached, farther out, past the orbits of the outer planets entirely, another structure waits in that same perpendicular direction, one shaped nothing like the thin, flattened disk of the planets, a vast, spherical shell of ancient debris surrounding the entire solar system from every angle, including the very direction Ulysses spent decades quietly exploring. By now, you have a picture forming in your mind, one that most people never take the time to build. A thin, crowded disk spinning around the sun, filled with planets, moons, asteroids, and drifting dust. And surrounding that disk, above it and below it, a quieter, emptier region, thinning out the farther you travel from the familiar plane. But here's the question worth sitting with for a moment. The question that gives this emptiness its true weight. Why is it actually empty? Not simply unexplored, but genuinely, physically lacking in the material that fills the plane so completely. To understand this, think back to the very beginning of the solar system. Back to that collapsing cloud of gas and dust we described earlier, flattening itself into a spinning disk as gravity and rotation fought for control. Almost everything that could have existed above or below that disk had already been pulled inward, crushed down into the flattening plane, long before the planets ever finished forming. There was no vast reservoir of untouched material left waiting above the disk patiently for something to happen to it. The raw ingredients simply were not there anymore, having already been swept into the flattened structure we now call the ecliptic. But formation alone does not fully explain the emptiness Ulysses measured so many billions of miles from Earth. Even after the solar system finished forming, small amounts of debris, dust, and fragments have continued drifting through every region of space surrounding the Sun, including above and below the main plane. Comets, disturbed from distant orbits, sometimes travel at steep angles relative to the ecliptic, scattering trace amounts of material outside the crowded plane as they pass. So why does this leftover material remain so much thinner outside the disk, rather than gradually filling in the emptiness over billions of years. Here's the thing most people don't realize about gravity's long, patient influence over time. Within the ecliptic plane, gravitational interactions between planets constantly nudge smaller objects, asteroids, comets, and fragments of debris into increasingly similar orbits, herding them gradually toward that same flattened structure. It is a slow, ongoing process, playing out across billions of years, gently sweeping material back into alignment with the plane whenever it strays too far from it. Outside the plane, perpendicular to it, no equivalent gravitational herd exists, because the very planets responsible for this shepherding effect are themselves confined almost entirely to that same flat disk. Think of it like a slow, cosmic version of gravity acting as a groundskeeper, tending endlessly to one particular garden while leaving the surrounding fields to grow wild and sparse. Anything that drifts too far above or below the plane experiences almost no similar gravitational tending, no repeated nudging back towards some organized structure. It simply continues outward, or falls back inward, along its own independent path, never accumulating into anything resembling the dense organized disk of material found within the ecliptic itself. Over billions of years, this leaves the perpendicular direction remarkably thin, almost stark, compared to the crowded plane just a short distance away. Here's a number that helps make this emptiness feel real rather than abstract. Within the plane of the asteroid belt, itself only a modest portion of the wider ecliptic, scientists estimate there are millions of individual objects large enough to track, ranging from tiny pebbles to bodies hundreds of miles across. Move even a relatively modest distance perpendicular to that same plane, and the density of comparable objects drops away dramatically. Not merely reduced, but genuinely, measurably sparse. It is the difference between walking through a crowded city street and stepping almost instantly into miles of open, empty countryside. And this emptiness carries consequences beyond simple curiosity about dust and debris. Consider, for a moment, what it means for the possibility of something approaching our solar system unnoticed. Within the ecliptic plane, we track objects constantly, watching for asteroids and comets that might someday cross paths with Earth, building ever more sensitive systems dedicated to spotting anything dangerous drifting through that crowded, familiar highway. Above and below the plane, in that same perpendicular emptiness Ulysses explored, our attention has always been far thinner, our instruments far less concentrated, simply because so little has ever been expected to arrive from that direction. Here's the thing that adds a quiet, unsettling undertone to this otherwise peaceful picture. Emptiness does not mean impossibility, it simply means rarity and reduced attention. Objects can, and occasionally do, arrive at our solar system from steep angles relative to the ecliptic, approaching from directions far outside the well-monitored plane where most of our search efforts remain concentrated. Because so little has historically approached from these perpendicular directions, our systems have never been built with the same vigilance toward them, leaving a quiet gap in our awareness, precisely where the sky feels, superficially, the most peaceful and the most empty. But let's return for now to the peaceful side of this same truth, because it deserves equal attention. The relative emptiness above and below our solar system's plane is also, in its own way, a kind of quiet gift. It is why our view of deep space, when we do manage to look perpendicular to the crowded ecliptic, tends to be remarkably clear, free from the scattering interference of nearby dust and debris. Many of our most distant, most breathtaking images of the universe, deep fields captured by powerful telescopes, benefit enormously from being aimed away from the cluttered plane, out into that same quiet perpendicular darkness we've been describing all along. So the emptiness above and below the ecliptic is not simply a void, devoid of meaning or consequence. It is a direct, physical signature of how our solar system formed, how gravity has shepherded material over billions of years, and how our own attention, our own instruments, our own search for danger and for wonder have been shaped by that same flattened structure. And as we continue travelling outward tonight, following that perpendicular direction, farther and farther from the sun, we are about to discover that this emptiness does not last forever. Eventually, far beyond the planets, it gives way to something else entirely, a vast spherical shell of ancient material surrounding our entire solar system in a shape unlike anything we have described so far. Far beyond the last planet, far beyond even the region Ulysses ever managed to explore, there is a boundary where the familiar shape of our solar system quietly disappears. The flat, crowded disk you have been picturing all night, the thin plane holding every planet in careful alignment, does not continue forever outward. At a certain distance, so vast it barely fits inside human comprehension, that shape simply stops. And something else begins instead, something that has almost nothing in common with the disk we have been describing since the very first chapter. Scientists call this distant structure the Oort cloud, named after the Dutch astronomer who first proposed its existence in the middle of the 20th century. He was trying to solve a puzzle that had nothing at first glance to do with the shape of the solar system. Long-period comets, the rare visitors that swing through the inner solar system only once every few thousand years, seem to arrive from every possible direction in the sky rather than from the flat, familiar band where the planets travel. If comets came only from the crowded plane, this pattern made no sense at all. Here's the thing that made this observation so quietly important. If these comets were arriving from every direction, not just from within the ecliptic, then wherever they originated could not be shaped like the flat disk we have spent so much time exploring tonight. It had to be something else. Something surrounding the solar system more evenly, in every direction at once, rather than confined to that same thin, spinning plane. Oort proposed that a vast reservoir of icy material must exist far beyond the planets, shaped not like a disk, but like an enormous, spherical shell. Think about how strange this shift really is, once you allow yourself to picture it clearly. Everything we have discussed so far, the planets, the asteroid belt, the dust, even the emptiness Ulysses measured above and below the ecliptic, all of it relates to that same flattened structure formed from the solar system's original spinning cloud. The Oort cloud breaks that pattern entirely. It surrounds the sun and everything orbiting close to it, not as a thin ring, but as a colossal, roughly spherical bubble, stretching outward in every direction, including the very perpendicular direction we have been following throughout tonight's journey. Here's a number that should feel almost impossible to hold in your mind. Scientists estimate the Oort cloud begins somewhere around 2,000 times farther from the Sun than the Earth is, and may extend outward as far as 100,000 times that same distance, reaching perhaps halfway to the nearest neighbouring star. To put that into perspective, if the distance from the Sun to Neptune could be measured on the scale of a single city block, the outer edge of the Oort cloud might sit somewhere on the other side of an entire continent, impossibly distant compared to everything we typically imagine when we picture our solar system. And within that colossal spherical shell, scientists believe, drift countless icy bodies, remnants left over from the solar system's earliest formation, gently disturbed just enough to occasionally send one plunging back toward the sun as a long-period comet. Trillions of these objects may exist out there, floating in near total darkness, far too distant and far too faint for any telescope to observe them directly. We know the Oort cloud exists almost entirely through its effects, through the rare comets it occasionally releases, rather than through any image we have ever actually captured of it. Here's the detail that connects directly back to everything we have discussed tonight about the perpendicular direction. Because the Oort cloud is roughly spherical rather than flattened like the ecliptic, it exists just as thickly above and below the plane of the planets as it does within that same plane. The emptiness Ulysses measured, that quiet thinning region perpendicular to our orbit, does not continue forever, all the way to the edge of interstellar space. Eventually, at a distance almost too vast to comprehend, it gives way to this vast, spherical shell of ancient material surrounding our entire solar system from every possible angle at once. This realization forces us to reconsider what we thought we understood earlier tonight. The direction perpendicular to our orbit is not simply empty all the way out, the way it might have seemed when we discussed the dust and debris studied by Ulysses. It is empty at moderate distances, within the region shaped mainly by the planets and their gravitational influence, but farther out, at distances so vast that light itself takes more than a year to cross them, that emptiness gives way to something ancient, something surrounding us evenly in every direction, including straight up and straight down from everything we have ever known. Here's the thing that should feel almost unsettling once you allow it to fully sink in. Somewhere out there, in that vast spherical shell surrounding the entire solar system, drifting in near total silence and near total darkness, there may be icy objects almost as old as the sun itself, waiting patiently for some distant gravitational disturbance to send them tumbling inward after untold thousands or even millions of years of near motionless drift. And because the Oort cloud surrounds us from every direction equally, some of that ancient material exists directly perpendicular to our orbit, just as much as it exists within the familiar plane of the planets. So the direction we have been following tonight, straight up and straight down, from the crowded disk we call home, eventually leads not into permanent emptiness, but into an entirely different kind of structure. A sphere rather than a disk, an ancient shell rather than a spinning plane. And as we continue exploring what this spherical shape actually means and how it changes our understanding of the solar system's true architecture, we are going to discover that the story of what lies perpendicular to our orbit is far stranger and far larger than a single flattened disk could ever fully explain. Take a moment to hold two shapes in your mind at once, side by side, the way you might hold two very different objects in your two hands. In one hand, picture the thin, flattened disk of the planets, the shape we spent so much of tonight carefully building, piece by piece, a shape thinner than paper compared to its width, spinning quietly around the sun, crowded with worlds and dust and comets, all confined to that same narrow plane. In your other hand, picture something entirely different, a vast, roughly spherical shell, so large it makes the disk look almost microscopic by comparison, surrounding everything evenly, from every direction at once. Here's the thing most people never quite grasp, even after learning about both of these structures separately. The disk and the sphere are not simply two different sizes of the same basic shape. They are fundamentally different kinds of structure, formed by entirely different processes, occupying entirely different roles in the architecture of our solar system. The disk formed from a collapsing, spinning cloud, flattened by rotation into the thin plane we have described so many times tonight. The sphere, the Oort cloud, formed from material scattered outward much more gradually, over a much longer period of time, disturbed and flung outward in every direction, rather than pulled inward into rotational alignment. Think about it this way. Imagine spinning a ball of wet clay on a potter's wheel, the same image we used earlier to describe the birth of the planetary disk. Now imagine instead tossing a handful of gravel outward from that same spinning wheel, scattering it in every direction rather than letting it settle into the flattened clay. The gravel would not form a thin disk the way the clay did. It would scatter outward, roughly evenly, forming something closer to a hollow spherical shell surrounding the spinning wheel from every angle. This rough analogy captures something true about why the Oort cloud looks nothing like the plane of the planets, despite forming from material that originated in the very same solar system. Here's a number that helps make this contrast feel real, rather than abstract. the plane of the planets, from the Sun outward to Neptune's orbit, spans roughly 2.8 billion miles. The outer edge of the Oort cloud, by comparison, may extend outward as far as 9 trillion miles, or even farther, depending on which estimates you consult. That means the spherical shell surrounding our solar system may be more than 3,000 times larger in radius than the entire flattened disk of the planets. A difference so extreme that the familiar solar system most of us picture becomes almost impossibly small by comparison. And yet, here's the detail that connects everything we have discussed tonight back to the perpendicular direction we began exploring so many chapters ago. Because the Oort cloud is roughly spherical, it does not favour any particular direction the way the flattened disk so obviously does. It exists as thickly above the plane of the planets as it does within that plane, and as thickly below it as anywhere else. The direction perpendicular to our orbit, the very direction most spacecraft have almost entirely ignored, is not somehow excluded from this vast ancient shell. It runs directly through it, just as much as any other direction radiating outward from the Sun. This means that if you could somehow travel in a straight line, perpendicular to the ecliptic plane, climbing directly upward from the flattened disk of the planets, you would eventually leave behind the relative emptiness Ulysses measured, and enter, after an almost unimaginable distance, that same vast reservoir of ancient icy material. You would not need to travel sideways, out along the familiar plane, to reach the Oort cloud. You would find it waiting for you directly overhead and directly underfoot, just as certainly as you would find it out along the plane of the planets themselves. Here's the thing that should genuinely surprise you. If you have spent your whole life picturing the solar system as a simple, flat diagram, that familiar image, the one you have seen in textbooks and planetarium shows since childhood, only tells part of the story, and arguably the smaller part in terms of sheer volume. The Oort cloud, spherical and vast, may contain far more total volume than the entire flattened plane of the planets, simply because a sphere naturally encloses so much more space than a thin disk of similar overall radius, once you account for every direction rather than just the familiar, crowded one. And within that enormous spherical volume, scientists believe drift countless icy remnants left over from the earliest days of the solar system, some of them perhaps larger than familiar comets we have seen streak briefly through our night sky. Most of this material has likely remained undisturbed for billions of years, drifting so slowly and existing at such vast distances that it experiences almost none of the warmth, light, or gravitational influence that shapes the busy, familiar plane closer to the Sun. It exists in near total darkness, near total cold, and near total stillness, a silent shell wrapped entirely around the small bright disk we call home. Here's a way to feel the true strangeness of this arrangement, one more time, before we continue our journey outward. Picture the entire flattened disk of the planets, the Sun at its centre, Neptune tracing its distant, lonely orbit at the outer edge, all of it shrunk down to the size of a single coin resting in the palm of your hand. Now imagine that coin suspended at the very centre of a hollow sphere the size of an entire room, its inner surface lined, faintly and sparsely, with ancient icy fragments drifting in near total darkness. That is the true scale relationship between the world you know and the vast quiet structure surrounding it from every direction. So when we ask what lies perpendicular to the Sun's orbit, the answer is not simply emptiness stretching outward forever into featureless darkness. It begins with emptiness, yes, a genuine and measurable thinning of dust and debris compared to the crowded plane. But it ends, eventually, in something ancient, something spherical, something that surrounds our entire solar system evenly, in every direction, including the very direction we have spent so much of tonight learning to finally notice. And this realization that our solar system's true shape is not simply a disk, but a disk embedded within a much larger sphere, opens the door to an even stranger question. If our own solar system is tilted and layered this way, What does that mean for our place within the far larger structure of the galaxy itself? Everything we have explored tonight has treated the solar system as though it exists in isolation, a lone disk and a lone spherical shell, floating quietly in an otherwise undefined darkness. But of course, our solar system is not actually isolated at all. It sits within a far larger structure, one so vast that the entire Oort cloud, despite stretching nearly halfway to the nearest star, still occupies only the tiniest, most microscopic corner of it. That larger structure is the Milky Way, our home galaxy, itself shaped, remarkably, in a manner strikingly similar to the flattened disk we described at the very beginning of tonight's journey. Here's the thing that should genuinely surprise you, once you allow yourself to picture it clearly. The Milky Way is not a random, shapeless scattering of stars, spread evenly through some enormous volume of space. It is itself a vast, spinning disk flattened for essentially the same reasons our own solar system flattened billions of years ago. A colossal cloud of gas spinning slowly, collapsed under its own gravity, and centrifugal effects held it out into a wide, thin plane. Exactly the same physics we described when the sun itself was forming from its own smaller, more localized cloud. Think about the staggering scale of what this actually means. Our entire solar system, the sun, the planets, the crowded ecliptic plane, the vast spherical shell of the Oort cloud, all of it exists as nothing more than a single, tiny point embedded somewhere within this much larger galactic disk. The Milky Way itself contains hundreds of billions of stars, spread across a disk roughly 100,000 light-years wide, so vast that light itself, the fastest thing in the universe, would take 100,000 years just to cross from one edge to the other. Here's the detail that connects directly back to everything we have been exploring about perpendicular directions and hidden shapes. Our solar system's own flattened plane, the ecliptic we have discussed so extensively tonight, is not actually aligned with the much larger disk of the Milky Way. It sits tilted at an angle of roughly 60 degrees relative to the galaxy's own flattened plane. This means that the direction perpendicular to our solar system's orbit does not point toward the same direction as perpendicular to the galaxy itself. The two directions, though related, are meaningfully different, layered atop one another like two tilted plates stacked slightly askew. Imagine, for a moment, holding that same spinning coin we described earlier, representing our solar system's flattened disk. Now imagine placing that coin, tilted at an angle, on top of a much larger, similarly flattened dinner plate, representing the entire disk of the Milky Way. The coin does not lie flat against the plate. It rests at a noticeable angle, its own perpendicular direction pointing somewhere quite different from the plate's perpendicular direction. This is essentially the relationship between our solar system's plane and the far larger plane of the galaxy surrounding it. Here's why this matters so much for the question we have been asking all night. When we imagine what lies perpendicular to the sun's orbit, straight up and straight down from the ecliptic, we are not simply pointing towards some fixed, universal direction. We are pointing toward a direction defined entirely by our own solar system's particular tilt, a direction that happens to angle away from the Milky Way's own flattened disk at a meaningfully steep angle. In other words, travelling perpendicular to our orbit does not just take you out of the crowded plane of the planets. In a very real sense, it also takes you partially out of the crowded plane of the galaxy itself. Think about what that layered geometry actually implies. The Milky Way's own disk, just like our solar system's ecliptic, is where most of the galaxy's stars, gas and dust are concentrated, crowded together in a relatively thin, busy plane, compared to the vast emptiness above and below it. Perpendicular to the galactic disk lies a region known as the galactic halo, sparsely populated compared to the crowded galactic plane, home to ancient, isolated stars and diffuse clouds of gas stretched thin across enormous volumes of space. And because our solar system's own perpendicular direction angles partway toward that same galactic halo, travelling straight up from our own ecliptic plane leads, eventually, into an increasingly sparse and increasingly ancient region of the wider galaxy. Here's a thought that might unsettle you gently, the way the best bedtime mysteries often do. If you could somehow travel far enough perpendicular to our solar system's orbit, farther than the Oort cloud, farther than any spacecraft has ever travelled or ever will, you would not simply arrive at more of the same familiar galactic disk, crowded with stars the way the night sky often appears. You would gradually enter a thinner, quieter region of the galaxy itself, populated by far fewer stars, illuminated by far dimmer, far more scattered light, stretching outward into the galactic halo, where our own Milky Way slowly fades into the emptiness of intergalactic space. So the direction perpendicular to the Sun's orbit turns out to be layered with meaning at every scale we examine it. At the smallest scale, it leads away from the crowded plain of planets and dust. At a larger scale, it eventually opens into the vast spherical shell of the Oort cloud. And at the largest scale of all, it angles, gently but unmistakably, toward the thinning outskirts of our entire galaxy, away from the crowded disk of the Milky Way and into a sparser, more ancient region few of us ever consider when we glance up casually at the night sky. Every layer, disk within sphere within disk, tilted against one another in a quiet cosmic geometry most people never learn to see. There is something you have never been told about your own motion through space, something so strange that most people go their entire lives without ever learning it. You are not simply standing still while the Earth orbits the Sun, and the Sun sits fixed at the centre of everything. The Sun itself is moving, carrying you, and every planet, and the entire flattened disk we have spent so long describing, on a long, sweeping orbit of its own around the centre of the Milky Way. And that orbit, remarkably, does not stay perfectly flat within the galaxy's own crowded plane. It gently rises and gently falls, drifting up and down like a slow, silent breath. Here's the thing most people never stop to consider. The Sun completes one full orbit around the centre of the Milky Way, roughly once every 230 million years, a span of time so long that the last time the Sun was in its current position, dinosaurs had not yet appeared on Earth. As it traces that immense slow circle, the Sun does not travel in a perfectly flat path confined to the galactic plane. It bobs gently above and below that plane, oscillating slowly, completing several of these gentle up and down cycles during each single orbit around the galaxy's centre. Think of it like a horse on an old carousel, slowly circling the centre of the ride while also rising and falling in a steady, rhythmic motion, up and down, again and again as the carousel turns. The Sun performs a similar motion on a far grander scale, rising above the crowded galactic plane, then sinking back below it, then rising again, over and over, across tens of millions of years for each individual cycle. Right now, at this very moment, the Sun sits slightly above the exact midpoint of the galaxy's flattened disk, drifting gently upward, perpendicular to the busiest, most crowded region of the Milky Way. Here's a number that might help this motion feel more real. Scientists estimate the Sun currently sits somewhere between 20 and 90 light years above the precise central plane of the galaxy, depending on which measurements and models you consult. A modest distance by galactic standards, yet still vastly larger than anything we discussed regarding our own solar system's Oort cloud. And this gentle drift, this slow rising and falling relative to the galactic plane, means that our entire solar system periodically travels through slightly different galactic environments, denser in some phases of the cycle, sparser in others. Think about what this means for the direction perpendicular to our orbit, layered now with this new, larger context. As the Sun rises above the galactic plane during part of its long cycle, our solar system spends time in a region with somewhat fewer nearby stars, somewhat less interstellar gas and dust, compared to when it sits deeper within the crowded galactic disk. We are not simply floating passively through a fixed, unchanging galactic neighborhood. We are slowly rising and falling through varying densities of stars and gas, carried along by a rhythm set in motion long before human beings existed to notice it. Here's a detail that some scientists find quietly unsettling, worth mentioning gently as we drift deeper into this cosmic geometry. A few researchers have proposed, though the idea remains debated and far from settled, that these periodic passages above and below the galactic plane might correlate with distant patterns in Earth's own geological history, including the timing of certain mass extinction events, spaced roughly every few tens of millions of years. The theory suggests that as the solar system rises or falls through denser regions of the galactic disk, gravitational disturbances might occasionally nudge distant Oort cloud objects inward, increasing, ever so slightly, the odds of a comet eventually crossing Earth's path. This remains speculative, an open question rather than settled fact, but it illustrates something profound about the layered geometry we have been building throughout tonight's journey. The direction perpendicular to our solar system's orbit is not simply a fixed, unchanging feature of our immediate cosmic neighborhood. It shifts subtly as our entire solar system rises and falls through the larger structure of the galaxy itself, carrying us gently between denser and sparser regions across cycles lasting tens of millions of years, far longer than any human civilization has ever existed to observe even a single, complete oscillation. Here's the thing that should feel almost dizzying once you let it fully settle in. We began tonight by discussing a fairly simple, almost geometric question. What lies straight up and straight down from the flat plane of the planets? And that simple question has carried us outward, layer after layer, first through the relative emptiness measured by a lone spacecraft, then through the vast spherical shell of the Oort cloud, and now into the slow, rhythmic rise and fall of our entire solar system through the wider structure of the galaxy itself. Perpendicular, it turns out, is not a single direction at all. It is a nested set of directions, each one revealing a different scale of the same underlying cosmic architecture. And above even this galactic rhythm, above the Milky Way's own crowded plane entirely, lies something else again. A thinner, quieter region called the galactic halo, sparsely populated by ancient stars and diffuse clouds of gas stretching outward into the true darkness between galaxies. As we continue our journey tonight, we're going to travel there next, into that thin, silent region perpendicular to the galaxy's own disk, to understand just how vast and just how quiet true interstellar and intergalactic emptiness can actually become. Let's travel now together, past everything we have described so far, past the crowded plane of the planets, past the vast spherical shell of the Oort cloud, past even the slow, rhythmic rise and fall of our entire solar system through the Milky Way's own flattened disk, climb higher still, perpendicular to the galaxy's crowded plane, and you eventually leave behind the busy, star-filled disk entirely, entering a region so different, so quiet, that it barely resembles anything we have described tonight. This is the galactic halo, and beyond it, the true silence of interstellar and intergalactic space. Here's the thing most people never truly grasp about the space between galaxies, even after learning about black holes, supernovas, and other dramatic cosmic events. The vast majority of the universe is not filled with stars, or planets, or glowing nebulae. It is filled with almost nothing at all. Vast ancient stretches of near-perfect vacuum, interrupted only occasionally by faint traces of gas, scattered dust, and the ancient, patient light of distant galaxies, travelling for millions or even billions of years before reaching any eye capable of noticing it. Think about what this means for the direction perpendicular to the Milky Way's own disk. the region we began approaching in the previous chapter. Within the galaxy's crowded plane, stars are relatively close together, at least compared to interstellar standards, with light from countless neighbours filling the night sky with a dense, glowing band we call the Milky Way, visible from Earth on sufficiently dark nights. Perpendicular to that plane, climbing up into the galactic halo and beyond, stars grow increasingly rare, increasingly isolated, separated by distances so vast that entire lifetimes could pass without a single one appearing to move relative to its neighbours. Here's a number that helps this emptiness feel real rather than simply abstract. The average distance between stars within the crowded disk of the Milky Way is measured in a handful of light years, close enough on a galactic scale to feel almost neighbourly. But within the sparse galactic halo, and further still within the true emptiness of intergalactic space, that average distance stretches out dramatically, sometimes by factors of 10 or more, leaving individual stars and galaxies isolated across gulfs of space, so vast that even light, travelling at its impossible, constant speed, requires millions of years just to cross the gap. Think about standing for a moment at the very centre of this silence, far above the Milky Way's crowded disk, perpendicular to everything busy and bright below you. Looking downward, back toward the galaxy's plane, you would see a dense, glowing band of stars, exactly the pale ribbon of light we call the Milky Way when we glimpse it from Earth on a clear, dark night. But looking outward, away from that band, into the true depths of intergalactic space, you would see something almost unbearably sparse by comparison. Faint smudges of distant galaxies scattered across the darkness, separated by gulfs of near-total emptiness stretching in every direction. Here's the thing that connects this vast, cosmic emptiness back to the humble little disk of planets we began tonight's journey exploring. Everything we have described, from the thin plane of the ecliptic to the spherical shell of the Oort cloud to the crowded disk of the Milky Way itself, exists as an almost unimaginably small dense exception carved out of an otherwise overwhelmingly empty universe. Wherever there is a disk, a sphere, a cluster of stars or planets, it exists as a rare pocket of structure and activity, surrounded on every side, in every direction, by emptiness so vast it defies ordinary comprehension. And this pattern, remarkably, repeats itself at every single scale we have followed tonight. Planets cluster into a thin disk surrounded by emptiness, surrounded by a spherical shell of debris, surrounded by more emptiness. Stars cluster into the thin disk of the Milky Way, surrounded by the sparse galactic halo, surrounded by the true emptiness of intergalactic space. Even galaxies themselves cluster together in vast thread-like structures, separated by enormous, nearly empty voids stretching across hundreds of millions of light years. Structure and silence nested endlessly within one another, echoing the same basic pattern from the smallest to the largest scales. Here's a thought worth letting settle gently into your mind as we drift deeper into tonight's journey. Perpendicular to the sun's orbit, perpendicular to nearly anything you can point toward in this universe, the honest answer to what lies in that direction is, overwhelmingly, silence. Not silence in the sense of complete absence, because faint traces of gas, ancient starlight, and scattered galaxies do exist even in the emptiest regions we have described. But silence in the sense of profound, almost meditative sparseness, a universe built mostly of vast, quiet distances, interrupted only occasionally by small precious pockets of structure, like the one we happen to call home. And this, perhaps, is the deepest and most calming realization to carry with you tonight. The emptiness perpendicular to our orbit, the emptiness perpendicular to the galaxy's own crowded plane, is not some unusual or frightening exception to how the universe typically behaves. It is, in fact, the ordinary state of nearly everything that exists. Our little disk of planets, our modest solar system, our entire galaxy full of stars, represent the rare exception, small islands of light and structure and life, surrounded on every side by an almost incomprehensibly vast and ancient silence, stretching outward, perpendicular to everything, in every direction you could ever choose to look. Let's return for a moment closer to home, back to our own solar system, and sit with a question that has been quietly waiting beneath everything we have discussed tonight. If the direction perpendicular to our orbit is genuinely thinner, genuinely emptier, and genuinely less monitored than the crowded plane of the planets, what does that actually mean for us here on Earth, going about our ordinary lives? Here's the thing most people never stop to consider. Almost every system humanity has ever built to watch for danger from space looks sideways, along the ecliptic, rather than up or down, perpendicular to it. Think about how we actually search for potentially hazardous objects, the asteroids and comets that occasionally cross paths with Earth's own orbit. Observatories around the world scan the sky night after night, tracking faint points of light that shift slightly against the background stars, revealing themselves as objects moving through our solar system rather than fixed, distant suns. But because the vast majority of asteroids and comets travel within, or close to, the same flattened ecliptic plane as the planets themselves, our search efforts have naturally concentrated along that same familiar band of sky, the same narrow ribbon we discussed all the way back in the very first chapter. Here's the thing that should feel quietly unsettling once you allow it to fully register. This means our attention, our telescopes, our carefully coordinated tracking systems are disproportionately aimed sideways, along the crowded plane, and comparatively less prepared for something arriving from a steep angle or from nearly directly above or below that same plane. It is not that such approaches are common. They are not. Most known asteroids and comets do, in fact, travel within a few degrees of the ecliptic, exactly where our search efforts are already concentrated. But rare exceptions do exist, and they deserve honest acknowledgement rather than comfortable dismissal. Think of it like a lighthouse, built to warn ships approaching from the open sea, its beams sweeping steadily across the horizon in a wide, familiar arc. That lighthouse does an excellent job protecting against threats arriving from the directions it was designed to watch. But it was never built to look straight up into the sky or straight down into the depths below the water, because no one ever expected danger to arrive from those directions. Our planetary defense systems function in a remarkably similar way, expertly tuned to the crowded plane where nearly everything has historically been found, and comparatively less attentive to the quieter, steeper angles perpendicular to it. Here's a number worth sitting with honestly, without exaggeration in either direction. Objects on highly inclined orbits, travelling at steep angles relative to the ecliptic, do exist, and some long-period comets originating from that distant, spherical Oort cloud we discussed earlier can approach the inner solar system from almost any direction at all, including nearly perpendicular paths. These objects tend to be rarer than their counterparts confined to the ecliptic, and they tend to move differently, often faster when they do eventually arrive, having fallen inward from such extraordinary distances under the patient, constant pull of the sun's gravity across thousands or even millions of years. This is not meant to frighten you as you drift towards sleep tonight. It is meant, instead, to add one more honest layer to the picture we have been carefully building since the very beginning of this journey. The direction perpendicular to our orbit is quieter, yes, and emptier, in most practical, measurable ways. But quieter does not mean permanently, absolutely safe from everything imaginable. It simply means less crowded, less frequently travelled, and historically somewhat less carefully watched, compared to the busy, familiar plane where astronomers have concentrated their attention for centuries. Here's the reassuring side of this same honest picture, worth holding on to as tightly as the unsettling side. In recent decades, humanity has begun expanding its search efforts well beyond the narrow ecliptic band, using increasingly sensitive telescopes capable of scanning much wider portions of the sky, including regions farther from the crowded plain than ever before. Survey programs designed specifically to hunt for potentially hazardous objects now sweep across far more of the sky than earlier generations of astronomers ever managed, gradually closing the gap between where danger has historically been found and where it might, in rare cases, still be quietly approaching from. Think about how remarkable that effort actually is once you consider it fully. We are not simply accepting the blind spot perpendicular to our orbit as an unavoidable fact of astronomy. We are actively working to close it, one careful observation at a time, expanding our collective vigilance outward into directions that, for most of human history, received almost no attention at all. It is a slow, patient project, much like the story of Ulysses, climbing laboriously out of the ecliptic plain, requiring extraordinary effort simply to look somewhere ordinary sideways. Observation had always overlooked. Here's the thought I want you to carry gently with you now. As this particular thread of our journey draws to a close, the universe rarely announces its dangers loudly, or from the directions we happen to be watching most closely. It requires patience, humility, and a willingness to look somewhere unfamiliar in order to truly understand the space surrounding us in every direction, not merely the crowded, comfortable plane we have grown accustomed to observing. And in learning to watch perpendicular to our orbit, we are not simply protecting ourselves from rare distant threats. We are also, quietly, learning to see our own solar system more completely, more honestly than we ever have before. Let's do something now that no human being has ever actually done, though we can still imagine it together with perfect clarity. Let's leave your body behind for a moment, drifting quietly in the dark, and imagine floating far above the solar system, far above even the highest point Ulysses ever reached, at a height equal to many times the distance between the Sun and Neptune. From up here, perpendicular to everything we have described tonight, turn around slowly and look back down at the home you have never actually seen from this particular angle before. Here's what you would notice first, and it might surprise you. The solar system would not look like the busy, three-dimensional model you have seen in textbooks and planetarium shows your entire life. It would look almost unbearably thin, a delicate, glowing ring of light, suspended in vast, silent darkness. The sun would blaze at its centre, small but brilliant, even from this extraordinary distance, surrounded by a faint, barely visible haze marking the orbits of the planets, so close together from this vantage point that individual worlds would nearly blur into a single, continuous line of light. Think about how different this view is from anything you have ever actually experienced standing on Earth's surface. From down there, within the plane itself, the solar system feels enormous, sprawling, endlessly complex, filled with individual planets, each demanding their own careful attention and study. From up here, perpendicular to everything, it collapses into something almost startlingly simple, a single glowing thread wrapped gently around a bright central point, floating quietly in an otherwise empty stretch of space, indistinguishable from sufficient distance from countless other similar threads surrounding countless other stars scattered throughout the galaxy. Here's a detail worth pausing on, because it carries real emotional weight once you truly picture it. Every war ever fought on Earth, every love ever felt, every civilization that has ever risen, and everyone that has ever fallen, all of it took place on a single small point, somewhere along that thin, glowing ring of light, so faint from this perpendicular vantage point that it would require instruments far more sensitive than human eyes simply to detect it at all. From out here, Earth itself would not even register as a separate point of light. It would exist only as an unimaginably tiny fraction of that already faint thread-like glow. And yet, here's the thing that should feel less frightening than it might initially seem, and more quietly comforting instead. Being small does not mean being unimportant. The fact that Earth would be invisible from this extraordinary vantage point does not diminish anything that has ever happened here, any more than a single grain of sand becomes meaningless simply because it cannot be seen from across an entire beach. Scale, in this sense, measures distance and size. It does not measure meaning or value or the quiet significance of a single, conscious mind capable of imagining this very view in the first place. Now, turn your attention away from that thin, glowing ring entirely, and look outward instead into the true darkness surrounding it, perpendicular to everything we have described tonight. What would you see there? Scattered points of light, distant and ancient, each one another star, many surrounded by their own planets, their own quiet dramas playing out on unimaginably small scales, utterly invisible from this same perpendicular vantage point, exactly as Earth's own history remains invisible from here. Countless threads of light, similar to our own, scattered across a darkness so vast it defies ordinary comprehension. Here's the thing that becomes almost impossible to hold in your mind fully, and yet worth trying anyway, gently, as you drift closer to sleep. Every one of those distant points of light represents another star, another potential solar system, another thin, glowing ring hiding its own history, its own small dramas, its own quiet grain of significance within an otherwise incomprehensibly vast universe. Perpendicular to our orbit, in this sense, does not simply lead to emptiness, or even to the ancient shell of the Oort cloud we discussed earlier. It leads eventually outward into a view of everything, an entire universe of similarly small, similarly precious points of light, scattered across darkness, on a scale no single mind can ever fully contain. And yet, remarkably, a single mind can imagine it, even if only briefly, even if only in fragments, the way you are imagining it right now, drifting gently toward sleep. This is perhaps the strangest, most quietly wonderful part of tonight's entire journey. The universe is vast beyond comprehension, filled with more emptiness than structure, more silence than sound, more darkness than light. And yet somewhere within that vastness, on a single small point, along a single, thin, glowing ring of light, a mind capable of imagining the entire structure, capable of picturing itself from 1 billion miles away, capable of feeling both smallness and wonder simultaneously, has somehow come into existence. Here's the thought to hold on to now, as we prepare to return, gently, back down toward that thin, familiar ring of light, back toward the small warm point where you actually exist. From out here, perpendicular to everything, our entire solar system looks almost impossibly delicate, almost fragile, a faint thread of light suspended in overwhelming darkness. But delicate does not mean insignificant. It means precious. It means rare. It means worth protecting, worth understanding, and worth quietly appreciating, especially now, as you drift closer to sleep, carrying with you this new perpendicular view of the small glowing home you have always called your own. We began tonight with a simple question, one you had probably never asked yourself before and might never have thought to ask at all. What lies perpendicular to the sun's orbit? Straight up and straight down, from the flat, familiar plane that carries Earth and every other planet quietly around our star. It sounded at first like a small question, a geometric curiosity, worth perhaps a passing thought before turning your attention to something else. But here's the thing most people never realize until they actually follow that question all the way to its end. Small questions, asked honestly enough and followed patiently enough, often unfold into something much larger than anyone expects. Think back over everything we have travelled through together since that first quiet question. We began with the disk itself, that thin, crowded plane holding the planets in careful alignment, formed billions of years ago from a collapsing, spinning cloud of gas and dust. We turned our attention perpendicular to that disk, discovering a region strangely emptied of debris, swept clean by the same physics that flattened everything else into place. We followed a single, extraordinary spacecraft as it climbed slowly and patiently out of that familiar plane, using the gravity of Jupiter itself to finally look down upon our own sun's hidden poles. And then, just when the story seemed complete, we discovered it was not. Beyond the emptiness Ulysses measured, we found the vast, spherical shell of the Oort cloud, ancient and largely unseen, surrounding our entire solar system evenly from every direction, including the very perpendicular direction we had been so carefully following. We zoomed outward further still, discovering that our own solar system's plane sits tilted against the far larger disk of the Milky Way, and that the sun itself rises and falls gently through that galactic plane across cycles lasting tens of millions of years, longer than almost anything human civilization has ever measured directly. Here's the thing that should feel almost breathtaking now, looking back over everything we have covered tonight. A single, simple question about geometry, about which direction happens to be perpendicular to our orbit, carried us outward through nearly every scale the universe has to offer, from dust and debris near our own sun, to ancient icy remnants at the edge of interstellar space, to the slow, patient rhythm of our entire solar system moving through the wider structure of the galaxy, to the true, overwhelming silence of intergalactic space itself, where entire galaxies drift like faint scattered islands across an otherwise nearly empty ocean of darkness. And through every single one of those scales, one pattern kept repeating itself, quietly, patiently, almost as though the universe were trying to tell us something about its own fundamental nature. Structure clusters together, tightly into disks and spheres and threads of light, surrounded on every side by emptiness far vaster than the structure itself. Our solar system, our galaxy, even the vast web of galaxies stretching across the observable universe, all of it represents the rare exception, small pockets of order and light scattered across an overwhelming, almost incomprehensible ocean of silence and darkness. Here's the thought I want you to sit with now, gently, as we begin to close this long, quiet journey together. You exist right now, on one of those rare, precious exceptions, a small, warm point of light and life, embedded somewhere within a thin, crowded plane, itself embedded within a vast, ancient spherical shell, itself tilted against the far larger disk of an entire galaxy, itself surrounded by an almost unimaginable silence stretching outward in every direction, including the very perpendicular direction we spent so much of tonight learning to finally notice. And yet, out of all that vast, overwhelming darkness, something remarkable has happened here, on this one small point of light. Matter arranged itself patiently across billions of years into something capable of looking outward and upward and perpendicular to its own tiny corner of existence, and actually beginning to understand the shape of everything surrounding it. You, drifting towards sleep right now, having followed this question from a simple flat disk all the way out to the true silence of intergalactic space, are proof of that remarkable achievement. You are the universe, quietly, gently, noticing its own shape. There is something deeply calming in that realization, once you allow yourself to feel it fully. The vast emptiness surrounding our solar system, surrounding our galaxy, surrounding everything we have discussed tonight, is not something to fear. It is simply the ordinary backdrop against which rare, precious pockets of structure and life quietly exist, our own small corner among them. Perpendicular to our orbit, perpendicular to nearly everything, lies mostly silence. But within that silence, here and there, scattered impossibly thin across incomprehensible distances, exist small points of warmth and light and consciousness, capable of imagining the very darkness surrounding them. Thank you for staying with me through this long, quiet journey tonight, following a single, simple question from the thin plane of our own solar system, all the way out to the true silence between galaxies. If you found yourself carried along by this same sense of quiet wonder, take a moment to like this video or subscribe so that more curious minds like yours might find their way here too. It helps this channel keep exploring these vast, gentle mysteries together, night after night, one question at a time. And now, as you finally let go and drift the rest of the way towards sleep, carry this thought gently with you. The next time you find yourself outside, looking up at the night sky, remember that you are not simply looking sideways, along the familiar, crowded plane of the planets. You're also looking, however briefly, into a direction perpendicular to everything, into a silence stretching outward, farther than any mind can fully hold. Sleep well tonight, and keep looking up at the stars.